Welcome to the 6.2 lesson video. Today we're going to be learning how to multiply and divide radical expressions, and that's our objective. So let's begin by talking about when a radical expression can be simplified. A radical expression can be simplified when the exponent of one factor of the radicand is a multiple of the radical's index. For example, if we have the square root of 12 and I want to simplify that, well, we know square roots typically don't have the index written in front. It's just assumed that you know that the index is 2 when we're taking the square root. If we wanted to simplify the square root of 12, I could break apart 12 into 4 times 3. And because I know that 4 is a perfect square, 4 is equal to 2 squared. And when we take the square root of something squared, we just get that number in the base. So that means 2 comes out because the square root of 4 is 2. We cannot simplify the square root of 3 because that exponent 1 is not a multiple of the index 2. Recall from Algebra 1 that it is possible to simplify the product of powers when those powers have the same exponent. For example, 2 squared times 3 squared is equivalent to the quantity 2 times 3 squared. And that's because 2 squared is equal to 4, 3 squared is equal to 9. When you multiply 4 and 9, you get 36. And when you multiply 2 and 3, you get 6. 6 squared is equal to 36. So that works. Similarly, if we raised 4 to the third, that would give us 64. If we raised 5 to the third, that would give us 125. If we took the 4 and the 5, multiply those bases, we get 20. And 20 to the third is equal to 8,000. And 64 times 125 is also equal to 8,000. So that confirms that we can simplify the product of powers when they have the same exponent. Similarly to that, we can simplify the product of radicals when they have the same index. Remember, the index is the little number in the top left-hand corner in front of the radical. So the square root of 2 times the square root of 3 is equivalent to the square root of 2 times 3, which is equal to the square root of 6. Similar to that, if we took the cube root of 4 and multiplied it by the cube root of 5, that is equal to the cube root of 4 times 5, which is equal to the cube root of 20. These ideas of combining radicals and powers will help us in today's lesson. The take note box in the middle generalizes this idea of combining radical expressions when we're multiplying them. So say we have the nth root of a and the nth root of b. If those numbers are real numbers, then when we multiply the nth root of a and the nth root of b, we get the nth root of the quantity a times b. In example 1, we're given a couple products, and we need to figure out if we can simplify the product of the radical expressions, and then we'll need to explain. So remember that in order to use the property of multiplying radicals, the radicals must be real numbers, and the indexes must be the same. So the number in the top left-hand corner must be the same for each of the radicals that we are multiplying. So in example 1, we have the cube root of 6, and we're multiplying the square root of 2. We are not able to simplify this product because the indexes are different. So that means the property from above does not apply. In part B, we're given the product of the cube root of -4 and the cube root of 2. Well, they are both cube roots, so that means the index matches, and we can multiply the numbers underneath the radicals. So we get the cube root of -8. This can be written as the cube root of -2 raised to the third, or cubed. And we learned this in the last section, that if we are taking the cube root of something cubed, or if the index and the exponent match, then we just get the number that we are raising. So that -2 would be the simplified form of the original product. Before we work through example 2, let's talk about what it means for a radical to be in simplest form. This means that the radical is reduced as much as possible. If the radicand of the expression, the nth root of a, has a perfect nth power among its factors, we can reduce this radical. So let's explore this idea in the following examples. We're going to take the square root of 24 and reduce it, and then we're going to take the cube root of 24 and reduce that. Let's think to ourselves, are there any perfect square factors of 24? Well, 4 is a perfect square factor, so we can rewrite 24 as the product of 4 times 6. And then we can rewrite 4 as 2 squared times 6. So the expression square root of 24 can be written as the square root of 2 squared times 6. So we can break that apart into the square root of 2 squared times the square root of 6. The square root of 2 squared is just 2, because remember the index and the exponent, when those two match, we just get the number that we have as the base. And then the square root of 6 cannot be reduced. So that means square root of 24 can be reduced into 2 square root of 6. Now let's take the cube root of 24. Let's think to ourselves, are there any perfect cube factors of 24? Well, 8 is a perfect cube factor of 24. So we can rewrite 24 as the product of 8 times 3. And now we can rewrite 8 as 2 cubed and then multiply by 3. And then break that radical apart into the cube root of 2 cubed times the cube root of 3. And just like the previous example, when you take the cube root of 2 cubed, you just get 2. And then we cannot reduce the cube root of 3, so that just comes over. So that means our simplified form of the cube root of 24 is 2 times the cube root of 3. In example 2, we need to simplify the radical expression, the cube root of 54 times x to the 5th. So what we want to do is write down all perfect cube factors, find those, and then group them together. I know that 27 is a perfect cube, and x to the 3rd, or x cubed, is a perfect cube. So I'm going to rewrite this as 27 times 2, that gives me 54, and x to the 3rd times x to the 2nd. From there, I'm going to rewrite 27 as 3 cubed, and then bring everything else down. From there, I would like to rewrite this radical as 2 radicals, the product of 2 radicals. So in the first radical, I'm just going to put everything that's a perfect cube. So 3 cubed times x cubed, because that's the part that I can bring out of the radical. The remaining part, 2x squared, will not be able to be reduced. So I'm going to keep that over in the right side. And you can notice for the first radical, the index and each of the exponents match. So that means I can take the cube root of 3 cubed and just get 3, and take the cube root of x cubed and just get x. So that expression pops out of the radical. The expression, the cube root of 2x squared, cannot be reduced. So that means my simplified form of the original expression, the cube root of 54x to the 5th, is equal to the product of 3x and the cube root of 2x squared. How do you know when you're done simplifying? We are done when the radicand, or the expression underneath the radical, contains no perfect cube factors. And let's just make sure, 2x squared does not have any perfect cube factors, so that means we are done simplifying this radical. Example 2 involved simplifying a cube root, so that means the index was an odd number. Recall from the previous section, 5.1, when we have an odd index, we do not need to use absolute value symbols for our answer. However, when we do have an even index, such as in the next example, we will need to consider where the absolute value symbol should go. Remember that in order to combine 2 radicals with the same index, in this case n in general, by multiplication, both radical expressions must be real numbers. So in example 3, we need to simplify the given product, the square root of 72 x to the 3rd y to the 2nd, and the square root of 10 x times y to the 3rd. Now when you're doing this, you can either simplify both expressions then multiply, or multiply and then simplify. In this example, I'm going to choose to multiply the radical expressions and then simplify from there. Remember that when you're multiplying radicals, you always want to check to make sure that the indexes are the same. And both of these radicals are square roots, so that means we can combine them by multiplication. So you can see here that I wrote this product of radicals as the radical of 2 products underneath. So now I'm going to multiply the like terms. So when I multiply 72 and 10, I get 720. And when I multiply x to the 3rd and x to the 1st, essentially, remember same base, when you're multiplying the same bases, you add the exponent, so we get x to the 4th. And then y squared times y to the 3rd is y to the 5th, because we added the 2 and the 3. So that means we get the square root of 720 times x to the 4th times y to the 5th. We want to simplify the square root of 720 as much as possible. So I wrote down the first 12 perfect squares, and I just tested out on my calculator different perfect square factors. And of course we want to choose the biggest one, because then we can do less simplifying after. So I tried 4, because I knew it was an even number. I got 180 when I divided by 4. I know that 4 goes into 180, so that means there's a bigger perfect square factor of 720. Next thing I did was I tried 16 because 16 is related to 4. When I divided by 16, I got 45. I know that 9 is a factor of 45, so that means 16 is not the biggest perfect square factor of 720. Next, I tried 144, and 144 actually fits into 725 times, and 5 does not have any perfect square factors besides 1, so that means 144 is the biggest perfect square factor of 720. So now I'm going to rewrite the radical expression as the product of perfect square factors and the leftover factors. So I'm going to write this as 12 squared times 5 times x squared to the second times y squared to the second times y. So you can see I have 12 squared, I have x squared, and I have y squared. Those are all perfect square factors. So now, just like in the previous example, I'm going to write this as the product of two radicals now. The first radical is going to have all my perfect square factors, and then my second radical is going to have the factors that are not perfect squares, so 5 and y. So that part will not be able to be reduced. So now I can take the square root of the first radical, and I just get 12 x squared y squared. Because remember, when you take the square root of quantities squared, those two just cancel out, and you just get the bases that were squared originally. And then the square root of 5y drops down. Remember, when simplifying an even root, we want to use absolute value bars to ensure that the root is non-negative. Since the original two square roots that we were working with were real numbers, x and y are non-negative by definition, so that means absolute value symbols are not needed in our final answer. Therefore, the simplest form of the product of the original radicals is 12x squared y squared times the square root of 5y. So far in this lesson video, we've been focusing on the product of radicals. Now we're going to talk about the quotient or dividing radicals. Since division is defined in terms of multiplication, we can extend the property of multiplying radicals to dividing radicals. And just as before, the indexes must be the same. If that's the case, we can write a quotient of roots as a root of the quotient. So we talked about the multiplying earlier, so now let's focus on dividing. So if we have the square root of 2 over the square root of 3, we can just rewrite this as the square root of 2 over 3. Similarly, if we're taking the cube root of 4 and dividing by the cube root of 5, we can write this as the cube root of 4 over 5. The take note box below generalizes this idea, and this idea is dealing with combining radical expressions, specifically using division or quotients. If we have the nth root of a and the nth root of b, and those are real numbers, and b is not equal to 0, then we can write the nth root of a divided by the nth root of b as the nth root of a divided by b. So remember, the indexes, or the little number in the top left-hand corner in front of the radical, must be the same in order to use this property. Example 4 gives us the opportunity to divide some radical expressions. So we need to write the following radical expressions in simplest form. So notice in part A that we have the square root of 18x to the 5th divided by the square root of 2x to the 3rd. They are both square roots. That means the index is 2 and the indexes are equal to each other. So we can write this as the square root of 18x to the 5th over 2x to the 3rd. From there, we can divide 18 by 2, that equals 9. And when you divide expressions with the same base, you are subtracting the exponents. So we have 5 minus 3, which is 2. So we have x squared. So the square root of 9x squared is the simplified form of the original expression. From there, we can simplify even further, because we could write this as 3 squared x squared. And when we take the square root of 3 squared, we just get 3. And when we take the square root of x squared, we just get x. You may be wondering, well, this is an even root, so should we be using absolute value symbols? No, we don't need absolute value symbols in this case because both expressions under the radical originally already required that x was not a negative number. Otherwise, we would have introduced imaginary numbers, which we're not going there in this chapter. So that covers the absolute value possibility here. So that means 3x is the simplified form of the original quotient. In part B, we're given the quotient of the cube root of 162y to the 5th and the cube root of 3y squared. So first thing I'm doing is I'm writing this quotient as the cube root of 162y to the fifth divided by 3y squared. From there, I need to simplify what's inside the radical. So I get 162 divided by 3 is 54, and y to the fifth divided by y to the second is y to the third. Remember, you are subtracting the 5 and the 2 to get 3. From there, I'm going to write this as the product of two radicals. Remember, the first radical contains the perfect cube factors. So I want to put 27y to the third, or y cubed. And in the second expression, or radical, we just have 2, because that's the leftover part that is not a perfect cube. I can rewrite 27 as the perfect cube 3 to the third, or 3 cubed, y cubed, and then drop down the cube root of 2. Remember, when we are taking the cube root of something cubed, we just get that base value, so we just get 3y. And the cube root of 2 cannot be reduced, so that comes down. So that means the original expression, or quotient, can be reduced to 3y times the cube root of 2. Another way to simplify a radical expression is to rationalize the denominator. And this means we would rewrite the radical so that there are no radicals in any denominator involved and no denominator in any radical. We have talked about this briefly so far this year, but now we're officially going over it. So here's an example that I suggest you write down in your notes. We have 1 over the square root of 2. In order to get rid of this radical in the denominator, we're going to use this process called rationalizing the denominator. And this entails multiplying the original expression by whatever radical is in the denominator. So you can see right here, we're multiplying by square root of 2 over square root of 2. The reason why we do it to the top as well is because we're essentially just multiplying by 1, because the square root of 2 divided by itself is just equal to 1. And when we multiply an expression by 1, we really aren't changing the final value, we're just changing how it looks. So 1 over square root of 2 is equal to square root of 2 divided by 2. Remember, when we're multiplying a radical by itself, we just get the number underneath because the radical cancels out. Example 5 gives us a chance to rationalize the denominator with a more complicated quotient. So we're given the expression, the cube root of 5x squared divided by 12y squared times z. The first thing that I notice is that we cannot simplify the expression under the radical. There's nothing that we can combine because there's no like terms. So what I do immediately is I write this as the quotient of the cube root of 5x squared and the cube root of 12y squared z. So I'm just splitting up the radicals. From there, I'm taking a look at the denominator and I'm thinking to myself, what do I need to multiply by this current denominator in order to make all of the factors a perfect cube in the denominator? So taking a look here, I have 12y squared z in the denominator. The first thing I do with that is I rewrite the 12 as the product of prime factors. This helps us determine what is needed to get a perfect cube. So I have 2 squared times 3, which is equal to 12, which we had originally, and then y squared and z stay the same. So 2 squared just needs to be multiplied by 2 in order to make that a perfect cube. 3 needs to be multiplied by 3 squared in order to make that a perfect cube. Y squared needs to be multiplied by y in order to make that a perfect cube. And z needs to be multiplied by z squared in order to make that a perfect cube. So we're not just going to be multiplying, but we're not going to be multiplying just by the bottom this time because that would not get rid of the radical. Instead, we're going to multiply the top and the bottom by the cube root of 2 times 3 squared times y times z squared. Remember, this process of rationalizing the denominator does not change the actual value of the fraction because we are multiplying by a factor of 1. Because these radicals have the same index, I can combine by multiplying. So I'm going to multiply the tops first. So I have 5 times 2 times 3 squared. Essentially, that's just 18. So 5 times 18 is 90. And then x squared comes down, y and z squared comes down. Those can't combine because all of those are different variables. So that's the top of my quotient. The bottom I'm going to combine. So I have the cube root of 2 to the third. Remember, we're adding the exponents of the like terms. 3 to the third, y to the third, and z to the third. That was the goal, was to get everything have an exponent of 3, so therefore they are perfect cubes, and we could reduce them in the next step. So the top is going to stay the same for the moment. 90 x to the second, y, z to the second. And then the bottom is just going to become 2 times 3 times y times z. Because we're all perfect cubes, so when we take the cube root of something that's a perfect cube, we just get the bases. So now we're just going to simplify a little bit further. The top still stays the same because there are no perfect cube factors of the expression under the radical. And the bottom is just going to become 6yz. So that is the simplified form of the original expression, and that means the correct answer was option A. That completes lesson 6.2. Make sure you write down all 6 lesson check problems. This gives you the chance to apply this knowledge that you just acquired during this lesson video. Please let me know if you have any questions the next time we meet, and I hope you have a wonderful day.